All right, welcome back. Your unit exam in this unit dealing with chapters 7 and 8. If you go back and look at the very first lesson we did, it's from chapter 6, but that was just a quick review of some trig to warm up your brain to trigonometry. Your unit exam is Thursday, so we're going to finish the unit today. We're going to be spending tomorrow and Wednesday reviewing. And that means your exam is Thursday. So then you have a 4-day long weekend, and we come back on Tuesday, and we'll get started on the final unit of Math 31. All of the problems that you were practicing from last lesson deal with applications of what we call natural growth or decay. I didn't really point it out to you, but it's natural growth or decay, and we use the natural base. So there's a reason why we call that base E the natural base. Anyway, you've got this property of natural growth and decay, which is the following. Growth is naturally occurring if the rate at which the population changes is proportional to the population. What does that mean in lay people's terms? It just means the more individuals you have in the population, the more reproduction of the organisms will occur. Or the more radioactive isotope nuclei that you have present, the more it can decay. Fewer you have, fewer decays. Anyway, in this formula, P equals P sub 0 times e to the kt. P sub 0 is the original population, or the initial population at time 0. E is the natural base. It's a constant. T is a variable. T is a variable, P is a variable. Let me highlight the variables because I got off track there and I don't know if I mentioned this or not. These two things are the variables. Everything else are either considered, well, they're constants, I guess, but E is a true constant. It's a number. Doesn't matter which exponential growth or decay problem you're solving, E has a value of E. The other letters, P sub 0 and K, are parameters. Okay? And those parameters define the type of growth or decay that's going on. Does anybody have any questions you would like me to go over from this? Liam? Certainly. Number 6. So we're being told that the population of the world is doubling about every 35 years. Let's keep something in mind that this is an out-of-date textbook. When we say in 1987 the total population is 5 billion, that's kind of our zero time mark. So what we're doing here is we're associating T with being 0, and we're connecting the year 1987 to that. And as a result of that, we can say the population at that point in time is 5 billion. I'm not using the middle column here mathematically. I'm not going to put the number 1987 into anything. It's just my benchmark for when we're starting. Looking at this, what I'm telling you, Liam, is that P sub 0 is 5 billion. And I think it's okay for us to just put 5 in for P sub 0. And we'll then basically build an equation where P is the population in billions. Okay. What is the projected world population in 2001? And what is the projected world population in 2100? And then as well, when will the population be 50 billion? So first of all, when we dissect question A, 2001 is 14 years after 1987. So if I take 2001 and subtract 1987, that means that we've got 14 years of growth. And what question A is saying, so this would be 2001 What question A is saying in part is what's this? And if I were to subtract 2100 minus 1987, I believe I'd get 113. So this is saying, and by the way, this is not a sustainable growth model. We know that. If you know anything about our world and the world we're living in, you cannot sustain this kind of doubling regularly. Something's got to give. There's not enough food. There's not enough resources. But based on this model, the other part of question A is saying this. So we need to fill in these two question marks for question A, and then for question B, the question is, what year or what time do we have to wait past 1987 to get 50 billion? And I'll be the first to admit here that I think if you solve this problem using a Math 30 approach, it would be a lot simpler. Okay, but I'm going to solve it this way. We have the formula population equals 5 billion times e to the kt, but we need to know the value of k. Now, I don't think this came up, but this first data point where I have t equals 0 and p equals 5, you can't use that to find k. Because if you put 0 in for t, that e to the kt becomes e to the 0 and k is gone. So we need to create a new data point based on this information. And by the way, shortly after 1987, this model was thrown out the window and it was doubling every 6 years or 7 years. So it's gone all over the place, but we're going to solve this as if it's a nice uniform type of growth. What we can say is that when t is 35, the population would be 10 billion. Because it tells you the population doubles every 35 years. It does say 35, doesn't it? Okay. So I'm going to put in 10 here for p, 35 in for t. This will allow us to find k, which cracks the case wide open. We'll be able to solve anything once we know k. Rearranging this, dividing both sides by 5 gives 2 equals e to the 35k. And if I take the natural logarithm of both of these, I wanted to just write 35k, but we've been away for a few days, so I'll remind you that when I take the natural logarithm of e raised to an exponent, I'm saying what is the base e logarithm of e to the 35k, which is me asking you to what do you raise e to get e to the 35k, and the answer is 35k. There's lots of ways for you to justify why the right side of this equation is 35k. Anyway, k is ln 2 over 35. And now we can build our equation. Our equation is the population as a function of time is the initial population times e to the kt, and k is the natural logarithm of 2 divided by 35. So as I said, this kind of blows the whole thing wide open and you can solve anything now. So I don't think I'm going to write a lot here for answering part A. We wanted to know when t is 14. So I'm going to take 5 times e raised to, in brackets, ln of 2 multiplied by the time of 14 divided by 35. You need to close the brackets after the 2. Otherwise, you'll be taking the natural logarithm of a lot more than 2. Answer times... No. Why do I have answer? I should have 5. Not sure where that came from. 5 times e to the ln 2 times the time over 35. And Liam, are you okay with me kind of rearranging where that 35 and the t are? Okay. This is what I get for the projected population in the year 2001. I don't know what the population in 2001 was. I think that could very well be close.
Just one question. When we're answering for multiple values of t, would you say it's easier to throw it in your calculator and use your table?
Yeah, and it didn't occur to me. What Evan is saying is, could we have just put this function in for y in the calculator and gone to the table? Absolutely. Yeah.
Since this is like people, do we have to like round up or
You know, that's unimportant. The question being asked right now is, do we round up or down? Or because I know we have this discussion in Math 30-1 that very often these population questions are how many complete years need to go by to reach that number. And if that's the way the question were worded, Ben, then you would have to round it up to 7. Even if you got 6.1, you would have to round it up. In this course, I'm not concerned about that. If this were a multiple choice question, then you would just have choices. If it were numerical response, it would probably say rounded to the nearest tenth of a billion. And if it were written response, then you would just round appropriately. You would round however you felt you needed to round and then justify it. So it's not a big deal. To get the one for 2100 is after 113 years of growth. So I'm simply going to go back in here, and instead of 14, it's 113. Make sure I have that formula right. So about 47 billion. I don't think that's sustainable, as I said. I don't. If you were to look at the population mapping on a graph for the past, say, 25, 35 years, it's pretty exponential until I think we hit about 2008, and then people started having less children, and the world changed slightly. If we wanted to know, let's finish this off now. We also wanted to know, and Liam, you had asked about this, right? So we would want to know when this is 50 billion. On the heels of what Evan said, I suppose you could plot that graph and also plot 50 billion and just see where they intersect. But that's a really good move when you have the technology. And some of you will take calculus courses next year that will employ technology. Most of you won't. Okay. You might employ technology here with computer programs to simulate different growth rates, but ultimately you should know how to do it on paper. So, we would have something like this, and you could find the intersection point, and I'm not really sure I want to show all of this work, but it'll only take a second. Or you would want to solve this equation. So when you divide both sides by 5, you get 10. It actually is not a lot of work to solve this. When I take the natural logarithm of both sides, I get ln of 10 equals ln of 2 over 35 times t. I'm the kind of person where I could probably solve this algebraically on paper a lot quicker than I could get the right window settings and everything set up. Ultimately, though, I can take 35 times ln of 10. And divide that by ln of 2. And this will be the time in years, which, we might want to actually, the time in years of growth, not the year date. Almost said star date. So 35 ln 10, close the brackets on that and divide by ln of 2. About 116 years. What was our answer at 2100? I thought it was over 50 billion. Oh, it's 46 or something. Yeah, yeah, okay. So if that's the length of time that elapses and we add that to 1987 as the starting year, you know, if that growth model was sustainable throughout that whole 100 and whatever years that was, it would be about 2103. Yeah.
Would this be the kind of question where we could justify rounding it to the year 2104?
I think that's kind of what Ben was asking about the rounding. That, yeah, you could. If the question said, how many complete years of population growth need to occur in order for the population to surpass 50 billion, then you would round it up to 117, regardless of how close it is to 116, because it says complete years. But again, I'm not so sure that I would ask it that way. I don't, in other words, it's unimportant for me in this course. In Math 30, it becomes important. Any other questions? Go ahead, Zebi. 7A. All right. So uranium has a half-life of 4.5 billion years. And what mass remains from a 100 milligram sample after T years? I want to make sure that you understand here. I'm going to let me rewrite this equation first. Are you okay, Zebi, with me customizing our population equation to just say mass? Okay. What this is saying is, what's the function for the mass remaining if you start off with 100 milligrams? So my mass is going to be in milligrams, and my time is going to be in years. I just want to set the record straight there. If I put in the initial mass for m sub 0, I have this, and I need to find the value of the constant k for this particular situation, which means that I need to put in a time in years. Well, you know what? Are you okay with me saying the time is in billions of years? I mean, we can put 4.5 times 10 to the 9, but if we just say the time is measured in billions of years, then we could just put 4.5. Okay. So we do have a data point, because if the half-life is 4.5 billion years, then when t equals 4.5, the mass is down to 50, because that's half of the 100. Does that make sense? Okay. So the half-life is the length of time it takes to get half of the mass. If we start off with 100 grams, half of that is 50. So now I can load those numbers in here and get 50 is equal to 100 times e to the kt. We divide both sides by 100 to get 0.5 equals e to the kt, but t is, I guess, I just want to back up here. I really ought to have put the 4.5 in for t when I put the 50 in for m. Doesn't really matter, I guess, but those two go hand in hand, right? These two are what we call in math an ordered pair. So when you have one, you get the other, right? That's the point. I can take the logarithm of both sides, the natural logarithm, and get ln of 0.5 equals ln of e to the 4.5 k. And ln of e to the 4.5 k is 4.5 k. So that means that our constant in our exponential decay equation is the natural logarithm of 0.5 divided by 4.5. And we had already loaded in the 100 for P0. I guess I'll stick with the M. We had already loaded in the 100 for M0. Now we just have to load in that ln of 0.5 over 4.5 for K. So it's 100 multiplied by E to that constant times T. Is that okay? Liam.
Would using years and billions be a bad idea if you are to move on to B and C? So that's for you to the mass remaining after 10,000 years?
I pondered that actually. What Liam is asking is, am I maybe setting myself up for difficulty by using billions of years? Because maybe I might be asked, what is the mass remaining after 10,000 years? And I did think of that, and I decided not to discuss it, because you wouldn't be asked for the mass remaining after 10,000 years, because it's such a small period of time compared to the half-life. You're basically left with almost 100 grams. So the times would typically be, you know, close to a half-life or more than a half-life. I don't know where this question is going. I stopped reading after A. Oh, it does say 10,000. Wow. I guess you got to multiply or divide 10,000 by a billion. Does it? I'm into a physics mode here though right now, and then we'll do that question. Does it make sense to you that it's going to be pretty close to 100 grams? I mean, 1,000 years, it's not even 1/10% of 4.5 billion years. What we could also do here, Liam, is we could just change our mind at this point and put 4.5 times 10 to the 9 here, right? But let's say we didn't. So I've made, it's not a tactical error, but a little bit of a tactical error in not looking ahead at what we were going to do. But if that time is 10,000 years, then to get it into billions of years, we have to take 10,000 divided by a billion. 1, 2, 3, 4, 5, 6, 7, 8. And I think I said it's not even 1%. I believe it is 1%. I believe that's 0.01. No, I don't think it is. Now I'm changing my mind again. A billion is 10 to the 9. It's not, you know, it's, I can't even wrap my head around those decimals. It's a very, very small proportion of a billion. Never mind the fact that the half-life is 4.5 billion. That would be what we would have for our time. So I'm going to load that number in here for the t. And just mathematically, I think it's important for you to understand that that exponent is going to be very tiny. So e raised to that exponent will be very tiny. It's going to be a little bit less than 1. But when we multiply by 100, we'll get pretty close to 100. Let's find out. Ln of 0.5 times that time divided by what other number do we have there? 4.5 is this. E raised to that is so close to 1. I've never noticed this question before. Times the mass. I'm actually surprised they're asking it. Maybe the point is so that we can have a discussion about the fact that that time is such a small proportion of the half-life, you wouldn't even notice anything missing. Kind of the opposite of what we'd talk about in Physics 30, where if we waited a million half-lives, there's nothing left. Is that okay? Have I answered your question now, Liam? And by the way, Zebi, I know you didn't ask about C, but if you want to know the rate of decrease after 10,000 years, you would have to determine the derivative, and the derivative would be dm dt equals this exponential function multiplied by the derivative of the exponent, which, you know, is a more meaningful thing to find. You know, how many nuclei are decaying per year at that point in time. And, you know, I there's that tactical thing again. If you put the time in billions, then what you will be finding is how many billions per year are decreasing. If you put the time, if you did the whole thing with years, then you would be finding how many per year. No, how many, no, I guess you're still finding decays, but it would be per billion of year as opposed to decays per year. All right, let's move on. So we have one more topic to cover. It is section 8.6 of your textbook, and it is called Logarithmic Differentiation. And I don't want you to confuse logarithmic differentiation with differentiation of logarithmic functions, which we've already learned. Okay, you know how to differentiate natural logarithmic functions. You know how to differentiate base 10 logarithmic functions. You know how to differentiate base any logarithmic function. That's not what this is about, although part of it involves differentiating logarithmic functions. This phrase, logarithmic differentiation, everybody, refers to a technique of differentiation. It's not a rule. It's not finding derivatives of logs, although it does involve that. The bigger picture is it's a method to find a derivative of something. There's two situations where you would use logarithmic differentiation. And one of them is a situation where you must use logarithmic differentiation. The other is a situation where if you're smart, you will use logarithmic differentiation, but you don't have to. Okay. So the first is if you have a function that you have no differentiation rule for. Okay. For example, the one I'm giving you here is y equals x raised to the sine of x. You do not have a rule for differentiating that. There isn't one. You have a rule for differentiating things like x to the 42. You can differentiate that with the power rule. It's 42x to the 41. That's the power rule. You have a rule for differentiating something like 3 to the x. It's 3 to the x, and I'm going to ask you for your help here to look at your formula sheet. 3 to the x ln 3. Okay. So we have a rule for differentiating a power where the base is variable, but the exponent is not. In other words, we have this rule for a variable raised to a constant. It's called the power rule. We have a rule for differentiating a constant raised to a variable. It's called the power rule. But we don't have a rule for a variable to a variable. So if I asked you to differentiate the following functions, y equals x to the x, which is a really weird thing to start wrapping your head around. Like, what does that even mean? It's bizarre. You would have to use logarithmic differentiation. If I said to you, find the derivative with respect to x of the sine of x raised to the natural logarithm of x, you don't have a rule for it. You would have to use logarithmic differentiation. And in the case of the one I'm dealing with in your note package, I've said x to the sine x. Yeah. I'm saying you cannot use either of these rules for y equals x to the sine x. You just can't. You must use logarithmic differentiation. The second case is you would want to use logarithmic differentiation, and you'll see how it works very shortly. You'd want to use logarithmic differentiation if it makes your job easier. Imagine that I said to you, differentiate that. I want to go sit at my computer and get a bunch of planning done, and I'm going to keep you busy for an hour. So differentiate it. It'll take you a very long time. And what would take you the most time is wrapping your head around how to apply the power, quotient, and product rules in your journey. It's almost impossible to keep track of. Because what you would have to do is wrap that 5 around that thing, and I'm not going to bother to write it, and raise it to the 4, and then use the quotient rule to multiply by the derivative of what's inside. Well, you're going to have the bottom squared here, which means it's going to have this to the 8, this to the 12, and this to the 6. But look at the rest of it. The derivative of the top times the bottom. Man, you got to differentiate the top, which is a product rule with chain rules at every stage. And then when you go minus the top times the derivative of the bottom, you have to differentiate the bottom, which is a product rule within a product rule. It's not navigable. You can't navigate through that. So you would use logarithmic differentiation there. And the way I describe it is you do have rules here, but who wants to do that? I mean, some of you might say, well, I don't even want to be here. I get that. But if you had some math to do, it would not be this problem, right? Not this way. So how do you differentiate logarithmically? You start off by taking the natural logarithm of both sides, and then you differentiate implicitly. And I can't believe that after all these years of teaching this, step 1 needs something more in there, I just realized. What you do is you take the natural logarithm of both sides to rewrite it where you don't have to use power rules. Or where you don't even have powers. For example, let's do this one. This is different than the one I just talked about. What this is y is equal to sine of x raised to the x. Like what? I don't even know. Your calculator might just kind of, smoke might start coming out of it when you do this. No, it won't. But I mean, let's take a peek. In brackets, sine of x, close all the brackets and raise to the x. And we have to be in radians, because that's the way it works. It being calculus. And I would try zoom 7, because that's trig. I have a feeling I know what's going to happen here. Sine of x is a periodic function which oscillates up and down between 1 and -1. But when you raise it to x, which gets bigger and bigger, that oscillation is going to start climbing higher and higher and higher. Well, there's something there. So if I change my window setting, I'm just intellectually curious here. I'm going to go up to 15 pi radians. I think that's more than enough. Whoops. From 0 to, say, 15 pi radians. I think I might have to go up incredibly high. Nope, I may be wrong here. I think it's falling because sine of x peaks at 1. So actually, it won't be falling, but it's going to be oscillating a little bit less, I think, in between. It's still going to reach 1 at every cycle because sine of x reaches 1. By the way, notice that there's parts where nothing is negative. which kind of makes sense. I'm going to, and again, this is just curiosity. Actually, you know what? I think it disappears wherever sine is negative. Like, you know where sine goes below the x-axis? If sine is negative, you can't have a negative base. I don't think there will be anything. And again, part of this course is for us to get thinking about math and patterns and relationships. Then we'll get back to the lesson. Enter. There we go. Yeah, I think it disappears. Wherever sine is negative, it disappears. There might be some other wiggling going on down there. Anyway, it's an interesting function. How do we differentiate it? Well, the first step says you take the natural logarithm of both sides. And I'm going to rewrite this that way. And once you see what's about to happen, logarithmic differentiation is really simple. Because we can move the x, that's the argument, that's the exponent of the argument, we can move this x out in front of the logarithm due to the power rule for logs. This has nothing to do with differentiation. We're simply moving it out in front. We get the natural logarithm of y equals x times the natural logarithm of the sine of x. And you can differentiate that. Because you know how to differentiate the natural logarithm of an argument. It's 1 over the argument, d argument dt, or dx. You know how to differentiate this because it's a product, and x is the first part of the product. You know what the derivative of that is, and you know that the derivative of the natural logarithm of sine of x can be found. I'm just going to throw this out because I feel I want to, and then we'll get back to it. How many of you see that the derivative of the natural logarithm of sine of x is cotangent of x? We'll come back to that in a second. So, differentiating left to right, we get 1 over y dy dx equals a product, derivative of the first times the second, plus the first times the derivative of the second, which is 1 over sine of x, times the derivative of sine of x, which is cosine of x. And that's where the cotangent's coming from, because cosine over sine is cotangent. I would probably do the next thing in one step, but I'm going to show 2 lines. 1 over y dy dx is ln of sine of x plus x cotangent x. Cotangent x is the cosine x over sine of x. So to get dy dx by itself, you can multiply both sides of the equation by y. And that's our answer. Well, I want to do one other thing, but that's it. It's a really bizarre, variables raised to variables are bizarre mathematical ideas. But to find the derivative, it's pretty simple. Any questions with that? There was a time, and it was, when I first started teaching this a long time ago, I was just out of university, and I had a prof that was very adamant about this. She would take off marks if you did not put your y back in. Was it sine of x to the x? Okay, I got it backwards. She would take off marks. She instructed her markers, her TAs, to take off marks if you didn't go, okay, now I'm going to put y back in. Well, I don't know. I've mellowed over the years where I kind of think what's the big deal? Because just make sure you follow this logic. If you were going to find a derivative, most likely it's to use the derivative, right? So maybe you want to find the slope of the tangent at x equals pi. Well, it's okay. You can use this. It's just that you have to go to the original function to find out what y is, then put that number in where I've marked it with a green arrow. I don't care whether you replace y with the original function or not, unless doing so simplifies it. You know, if by some bizarre twist of fate you got for a derivative, totally different question. This is not going to work, but that's okay. I'll just pretend. For some reason, you got this for a derivative. And y happened to be x to the sine x, which it couldn't be, but if it could simplify, you would do so. Always keep that in mind. All right, let's try another one. So differentiate this. So this is the second case where you could use all of the rules at your disposal to find the derivative, but it's too complicated to do so. I want to point out something to you. When you have this situation and you use logarithmic differentiation, you're probably not going to spend any time simplifying the result. Okay? You're going to leave the result in this weird form that you'll see. So let's rewrite this. Y is equal to x sine x over x squared minus 1 raised to the third. I take the natural logarithm of both sides. And that allows me to move that exponent out in front. If I move the exponent in front, I get ln of y equals 1/3 ln of x sine x over x squared minus 1. Any questions to that stage? Now there's, maybe just drop your pencil for a second. There's many different things you can do here. Traditionally, the way this is taught, and I don't know why this is the case, so don't write this down. This is then written as 1/3 times the natural logarithm of x plus the natural logarithm of sine of x minus the natural logarithm of x squared minus 1. In other words, we're breaking down the logarithm and saying the logarithm of a product is the sum of the logarithms. The logarithm of a quotient is the difference of the logarithms. You're with me on that, I hope. That's like saying ln of a b over c. And I'm just doing this to make sure you understand this step, is equal to ln of a plus ln of b minus ln of c. Right? That's what we're talking about here. And what textbooks and profs and teachers traditionally do then is they, and you're not writing this down again, is they go 1 over y dy dx equals, and then they invoke the constant multiple rule for derivatives, which is that the derivative of that constant of 1/3 times that big function is 1/3 times the derivative of all of those. And as a result, you get that 1/3 kind of just tagging along everywhere. And I don't like that. And then I've seen some people bring that third down and put it in everything, which means it's tagging along as well. But Why don't you get rid of the third at this point in time? Why don't you multiply both sides by 3 and you're not dealing with a fraction? So now I have 1 ln y times 3. I'm going to get 3 ln y equals ln of x plus ln of sine of x plus ln of x squared minus 1. And to me, that's nicer. Now, I haven't differentiated anything yet, right? By the way, just realized I should probably change this example next time I build this unit. You know, if this were x to the 4, then you would have a 4 in front of the ln of x. So we could differentiate here if you like. It doesn't matter. Some of you might have the clever idea, and it is clever, of moving that 3 up as an exponent on y, but you'll see why it doesn't matter in a minute. The derivative of 3 ln y is 3 times 1 over y dy dx. If you move that 3 up top, and you had ln of y cubed, and you differentiate this, you ddx it, you're going to have 1 over y cubed times 3y squared. You're going to get 3 over y dy dx, which is what we have, right? You would also have a dy dx here. So strangely enough, moving that 3 up as an exponent on y, I think, makes things weirder to think about. All right, let's continue with our differentiation. Equals the derivative of ln of x is 1 over x, plus the derivative of ln of sine of x, which of course is cotangent of x, but we won't make that jump every time. 1 over sine of x times the derivative of sine of x is cos of x, plus the derivative of ln of x squared minus 1 is 1 over x squared minus 1 times 2x. So dy dx is equal to this thing, I think that should be minus, shouldn't it? Is that what you were going to just tell me, Ben? Yeah, it should definitely be minus because it was in the denominator. And I don't know at what point I lost that, but I know when I was doing the don't write this down, I put minus, but I must have switched it. It's definitely minus. So then minus 2x over x squared minus 1. Now, I mean, you could make the argument, now we move this 3 back over, so there's the third. We didn't really need to move it out of the way to begin with. We could have kept it there. And then we also have y. And that's it. So, and that is it. I'm about to talk a little bit more about this, but we're not changing anything. Does anybody have any questions with that example? Okay. See, I mentioned that you don't want to simplify this. And if you did simplify this, you would have to put this over, and I would actually change this to the following, if I was going to do this. You would have to put it over the common denominator. Now just think about what would be involved in converting all that to a common denominator, and what a mess you would create. That mess that you would create would be the mess that would come out of differentiating this normally. And the work that you put into this bottom line to bring it all together would be the work that we're trying to avoid by using logarithmic differentiation. We don't want that. We're done here. That's where you end it. Now we've got a functional derivative, which means we can use it to calculate things. That's it. You can see you've got some practice here, questions 1 to 3. I'm going to see if I can get some review material in your hands today before the end of the class so that you can get started on some review. And Demi and Zach, I will email it over to have somebody print it out for you. Okay.